So in a moment, we're going to begin a discussion of measures of the strength and direction of association between categorical variables. And so the attributable risk, the risk ratio, and the odds ratio. A few things to say before we get into that is that we really want to make a note here that we probably should not be doing this simple 2x2 table analysis at this point, as we know that the estimate we get from that 2x2 table analysis is going to be biased. We know that there's these other confounding variables. So we've already touched on this, and let's just quickly remind ourselves of that. This variable, would you like to have more children, yes or no? Okay, it's an important confounder here. So I've already drawn the diagram out here this is the diagram that represents confounding, right? We can think this variable, do you want more children, yes or no? It should be related to contraceptive use. This desire to have more children or not is likely associated with level of education. Those who have higher level education tend to have fewer kids. Those with lower level education tend to have more kids. And you can imagine if you drew in this age category variable and placed it where the want more children is, it'd fit the same conceptual diagram. Okay, so age category seems to be a confounding variable as well. So really, if we're going to do this analysis, what effect does education have on contraceptive use? We're going to need to adjust for these confounders. But for now, for the sake of discussing some of these measures of association between categorical variables, we're going to ignore the fact that these estimates are biased and that we're not adjusting for confounding. And so we'll talk about, for example, what is an odds ratio, how is it calculated, what's its interpretation, and so on. And then later we'll see through using logistic regression, we can calculate the odds ratio, but adjusted for confounding factors. Right, so what effect does education have on contraceptive use, adjusting for whether or not they want more children and what their age category is. I'm also going to mention quickly here that I'm going to go through and talk about the attributable risk, the risk ratio, and the odds ratio. On the course website, there is linked to a separate video that goes over all these measures as well. So if you find that the explanation I provide here isn't enough and you want a little bit more, you can take a look at that video that's already linked to on the website, going through a similar explanation with a bit more detail. So the three measures we're going to talk about are the attributable risk, or sometimes it gets called the risk difference, the risk ratio or rate ratio, as well as the odds ratio. And these all measure the direction and strength of association between categorical variables. And actually, as we progress on, we'll see the X variable can be numeric. It doesn't need to be categorical. We'll also mention, I'm going to use the word risk ratio and rate ratio interchangeably. There is a slight difference between the two, and later on, we'll try and separate exactly what the difference is between a risk ratio and a rate ratio, but they're very similar in concept, and so a lot of people tend to use them interchangeably. And so there is a slight difference between the two, and we'll explain what that is shortly. One note that we should make before we get into all these is that you should not calculate the risk difference or the attributable risk, as well as the relative risk or risk ratio or rate ratio. So that's one other name I forgot to throw in there. So the RR, sometimes it's called the risk ratio, the rate ratio, or the relative risk. The nice thing is they all abbreviate RR, and they all mean pretty much the same thing, so they tend to get used interchangeably. We should not calculate either of these, the attributable risk or the risk ratio, if our data comes from a case control study. And so this essentially means if the prevalence in the study does not represent that of the population. And again, we'll talk a little bit about study designs and their implications in a few more slides, once we get through talking about these measures. In this kind of data, where we're thinking of a 2x2 table data, there's generally two probabilities that we're interested in comparing in some way. We want to compare what's the probability of using contraceptives given the woman's of high education, and we want to compare that to what's the probability of using contraceptives if the woman is of low education. Right, so again, what's the probability of contraceptive use for someone of high education, and we want to compare that to that same probability but for someone of low education. So using the generic terminology, we're going to label this as the probability of disease given exposure, and we want to compare that to the probability of disease given non-exposure. Okay, so that's what that e to the power of c means. okay, not exposed. Okay, and so again, level of education is not an exposure or not, and using contraceptives or not is not a disease. So these are the generic terms that gets used. Relationship between exposure and disease. Okay, so looking at the data that we have, the two probabilities that we want to compare, well, the first is the probability of disease given exposure, right? That's the generic statement. Or what's the probability of using contraceptives given the education level is high? And we can see in this table, for those of high education, there's 994 individuals, right? In that top row, there's 994 individuals who have high education, and of those 994, 306 are using contraceptives. Okay, so this probability comes up to 30.8%. Now, we want to compare this to the probability of disease for someone who's not exposed. Okay, or in our example, what's the probability of using contraceptives if education is low? And we can see in that second row, right, those who are low education, there's 613 in total. Of those 613, 201 are using contraceptives. Okay, so 32.8%. Okay, and so again we can see of those who are highly educated, 30.8% are using contraceptives. Of those with low education, 32.8% are using contraceptives. Okay, so we want to compare these two numbers to each other in some way. And again, a reminder that later we're going to acknowledge we need to adjust for other confounders. Right? Comparing these two directly isn't completely fair because there's other confounding factors in there. But let's just stick on the measures for now. So if we want to compare these two probabilities to each other, how can we do that? I'll give you a second to think about it, and then I'll shout out an answer. Okay, here comes the answer. If you want to think about it for another minute or two, just give the video a pause. But comparing this probability of using contraceptives for someone who's highly educated relative to someone who's lowly educated, we can either take the difference in those two numbers or take the ratio of those two numbers. Okay, so those are two of the measures that we're going to look at. So the first one, the attributable risk, or sometimes what gets called the risk difference, is the difference in those two probabilities, right, or the difference in those two risks. What's the probability of using contraceptives given someone's highly educated minus the probability of using contraceptives given they're lowly educated? Or that 30.8% minus the 32.8%, which gives us negative 2%. And so again, here we can say the likelihood or the probability of using contraceptives decreases by 2%, right, for someone who's highly educated relative to someone who's lowly educated. Here, someone of high education is using contraceptives 2% less than someone of low education. And again, we acknowledge that this is a bias estimate. We'll address that in a little bit. The second measure is we can calculate something called the risk ratio or a rate ratio, or sometimes it gets called a relative risk. So this is a ratio of those two numbers. Right, so again, it's a ratio of what's the probability of using contraceptives given someone's highly educated divided by the probability of using contraceptives given they're lowly educated. That's the 30.8% divided by the 32.8%, which comes out to 0.94. Okay, again, there's a lot of ways this can be interpreted. We'll go through a few of them as we progress through these ideas. But we can say that the likelihood or the chance of using contraceptives for a woman with high education is 0.94 times the chance of using contraceptives for someone of low education. Or we can say that women of high education use contraceptives 94% as often as a woman of low education. Or if we subtract 1 from that, we can think of it as a percentage change. So the 0.94 minus 1 gives us negative 0.06 or negative 6%. So women of high education are using contraceptives 6% less than a woman of low education. And again, this is on a relative scale or a multiplicative scale. Through some other examples, we'll talk about what's the difference between the attributable risk and the risk ratio, or what do we mean by looking at the difference on an additive scale versus on a relative scale. So we'll look at a few examples to try and tease those two apart. The final measure is the odds ratio, and this is a ratio of the odds of disease given someone's exposed relative to the odds of disease given they're not exposed. Okay, or in other words, it's what's the odds of using contraceptives for someone of high education divided by the odds of using contraceptives for someone of low education. And remember, we're not going to focus on calculating these by hand, so I don't want you to get too stuck on the formulas that are being shown here. But we're going to separate the idea that in English, we use the words probability or odds interchangeably. Mathematically, they're not the exact same thing. Okay, so this is the quick overview. We're going to expand on each of these a little bit, and I'm also going to mention a reminder that there is this separate video that goes over all three of these in a little bit more detail. So that's already up on the website, as I mentioned, but here's the link to it. In the video, the hyperlink won't work, so you can type that in if you want, or like I said, on the course website, it's there. It's on my YouTube channel. It's going to be a video called Attributable Risk, Risk Ratio, and Odds Ratio, or Measures of Association Between Categorical Variables. So there are some assumptions necessary for calculating the attributable risk, the risk ratio, and the odds ratio. We've already touched on these, but one thing you'll notice through the previous course and this course is that all of these methods have certain assumptions that are necessary, and they're all pretty similar with a few minor differences depending on are the variables categorical or numeric and some things like that. But for the most part, the theme is generally the same. We're always assuming that observations are independent, so person 1, person 2, person 3, and so on. They're all independent of each other. We're assuming that the sample size is large in some way. Right? How we define large changes a little bit, but that theme is always there, that there's a large sample. And again, a few others depending on the exact method. Right? Constant or equal variance was an assumption in the two-sample t-test, and analysis of variance. We assume linearity for linear regression, and a few others that change slightly. Independent observations, large sample, those are always there. So it's important that these assumptions are met, or at least reasonably met, if we're going to use these methods. Okay, in reality, assumptions are never perfectly met, but we want to be able to assume that individuals are independent enough that we can work with it. Okay, our sample size is large enough that we can work with it. A quick note on the difference between odds and probability. As we said, in English, we use the two words interchangeably. What's the probability of winning a game? What are the odds of winning a game? What are the odds of that happening? Right? We say odds and probability interchangeably, although mathematically they're not the exact same thing. There's a video you can watch. The link's there. It's quite long, but it's linked to on the course website, so you can check that there. What that video is, it explains the difference between probability and odds, and it came through actually a clip in the Big Bang Theory where Sheldon was talking about, he wanted to talk about probabilities, but he's calling them odds, and I just thought it was funny catching Sheldon, who always nitpicks on things, using these words incorrectly. Because probability and odds are not the same thing, the RR and the OR are not the same thing. The RR is a ratio of probability of disease for exposed over probability of disease for unexposed. The odds ratio is the odds of disease for exposed divided by the odds of disease for not exposed. Let's just get into the difference between probability and odds. If the probability of something happening, if the probability of A occurring is 0.75 or 75%, then the odds of A occurring are the ratio of the probability A happens to the probability A does not happen, or the 75% divided by 25%. It's a ratio of occurrences to non-occurrences. A happens 75% of the time, it does not happen 25% of the time. And if you look at that, it's going to be 3/4 divided by 1/4, right? Or 3/1 or 3:1. So for every 3 times A occurs, there will be 1 time it does not occur, right? Or A happens 3 out of every 4 times. Okay, so they convey similar information. If you know the probability, you can find the odds. If you know the odds, you can find the probability, but they're not the exact same thing. Similar to if the probability of A occurring is 33%, the odds of A occurring are 33% over 66%, or it's going to be 1/2. 1 occurrence for every 2 non-occurrences. For every time that A occurs, it will not occur 2 times, right? Or A is going to occur 1 out of every 3 times. Okay, so again, they're very much related. Knowing one tells you what the other one is, but they're not the exact same thing. Okay, so just a quick reminder of the idea of incidence versus prevalence. So this is a concept you would have learned about in EPI. Prevalence is looking at how many cases of the disease are there in the population at a particular point in time. The incidence is the rate at which new cases of the disease are happening. Kind of the classic diagram for this is if you think of a bathtub filling up with water. Okay, the prevalence tells us how much water is in the tub at a given point in time. Just like the prevalence of a disease, what percentage of a population has a particular disease at a point in time. The incidence is the rate at which new water is being poured into the tub. Right? Again, the incidence rate for a disease is what's the rate at which new cases of the disease are developing, okay, or the rate at which people are getting the disease. And so again, the prevalence is the entire pool of people who have the disease. And the only way people leave that disease state is either they can recover from the disease, okay, and that's shown through water evaporating out of the tub, or they can die, right, and that's shown through water leaking out through the drain. Okay, so again, prevalence of a disease and incidence of a disease are both important measures, and they tell us slightly different things. Okay, so one thing to remember, for a cross-sectional study, right, this is where we take a survey of individuals at a point in time, we can estimate the prevalence, right? If we give people a survey and ask them, do you have some condition, yes or no, right? We can estimate what proportion or what percentage of the population has that disease. That would tell us the prevalence. Okay. Then if we want to calculate the attributable risk, we're going to take the prevalence of the disease for exposed minus the prevalence of the disease for unexposed. Or we can take the ratio of those two. Right? What's the prevalence of disease given you're exposed divided by the prevalence of disease given you're not exposed. Okay, so we can calculate the attributable risk or the risk ratio. Now, for a cohort study, this is where we follow people over time. Right? We start following people at a certain point in time, and we follow them continuously over time. In this sort of study design, we can estimate the incidence. Right? Because we have that time component, we can see at what rate are people contracting the disease, right? Or how often are we getting a new case of the disease. Okay, so for cohort designs, we estimate incidence, and we can still calculate these two measures. The attributable risk would be what's the incident rate of disease for exposed minus the incident rate of disease for unexposed. Or we can take the ratio of those two. What's the incidence, right? And this would be the RR. What's the incidence of disease for exposed divided by the incidence of disease for unexposed? Okay, so this is where the risk ratio and rate ratio, the slight difference between the two. Okay. If it's a ratio of prevalences, sometimes it gets called the risk ratio, or might get called the prevalence risk ratio. If we have incidence data and we're taking a ratio of incidences, it sometimes gets called the rate ratio or the incidence rate ratio. Okay, but as you can see, they're pretty similar whether we're looking at a ratio of prevalences or a ratio of incidences. So that's why people tend to just use the terms interchangeably. Now, for a case control study, right, this is where you select people with the disease and people without the disease, and then you ask about their exposure. For this design, we cannot estimate the prevalence or the incidence. Right? So if we're selecting people who have the disease, let's say we get 50 people with the disease, 50 people without the disease, and then we ask them about their exposures. We can't use that data to estimate prevalence. Right? We've selected how many people have the disease and how many don't. We also have no time component in this design, so we cannot estimate the rate at which people are contracting the disease. Right? We've just selected 50 with and 50 without. So for this sort of design, we cannot estimate the attributable risk or the risk ratio. Now, the study designs for this course and for the assessment, you're not going to be assessed on these, so this is all that you need to know. But if you'd like a little bit more, if you go on my YouTube channel, there's a video there about study designs, observational data study designs, or study designs in health research. So it's going to talk a little bit more about cross-sectional designs in cohort and so on. But the key takeaway here is that if we have cross-sectional design or a cohort, we can estimate the attributable risk or the risk ratio. If we have a case control study, we cannot estimate either of those. Okay, and that's where the odds ratio comes in. Okay, we can estimate an odds ratio for these designs. So just to kind of recap that, we've just noted that we cannot estimate prevalence or incidence if we have a case control design. And so we cannot estimate the attributable risk or the risk ratio. Okay, but we can estimate an odds ratio for a case control design. And I won't get into discussing why that is, but again, I'll put a link on the website to a video that explains why you can estimate an odds ratio for a case control design. And it's not going to be part of the assessment for this course, but for anyone who's interested, I'll make sure that link's there so you can view that if you'd like to. But so one of the nice kind of circles we get into is that for a case control design, we can only estimate an odds ratio, but we also find that if the prevalence or the incidence of the disease is rare, so if we're working with rare diseases, then the odds ratio is approximately equal to the rate ratio. And also, the time when we use case control designs is quite often in the case of a rare disease. If a disease is quite rare, we might just need to take people who have the disease, people who don't, and try and study them, rather than, say, using some cohort design where we're following people for years and not many of them will get the disease because we're studying a rare disease. Okay, so this is kind of the nice loop we get in. The RR is kind of a nicer thing to know. If we have case control design, we cannot estimate that. We can only estimate an odds ratio. But the odds ratio is approximately equal to the RR in the case of a rare disease. And rare diseases are where case control designs are most often used. Okay, so the point of this is, in a case control study, which is usually going to be used for a rare disease, we can only estimate the odds ratio, but that's approximately equal to the rate ratio. So we can interpret that odds ratio the way we'd interpret the rate ratio. Okay, so here's just some things that you can work through if you want some practice. Again, in the course, we're not going to work on calculating things by hand, so I don't want you to get stuck in the formulas. This was really intended to show something. Okay, and I'll get into what that is in a second. So we're going to look at working out the attributable risk, the risk ratio, and the odds ratio in these three cases. Okay, when the probability of disease for someone who's exposed is 2%, and the probability of disease for someone who's not exposed is 0.5%. Part B, when the probability of disease for exposed is 40%, and the probability of disease for unexposed is 10%, as well as when the probability of disease for exposed is 80% versus 20% for someone who's not exposed. On the next slide, I'm going to show you the answers to those and we'll talk about them. And given just the time pressure we've been under with COVID-19 to get all these video lectures recorded and online, you'll see that this slide here is just some stuff I wrote on a piece of paper and took a picture of with my phone and put up here. So it's not as nice as I'd usually like for presentation, but it's functional and it's working. In example A, the attributable risk is that 2% minus the 0.5%, which comes out to 1.5%. So what we can say is someone who's exposed to the risk factor, their probability of disease goes up 1.5%. And again, this is on an additive scale, meaning it goes from 0.5% up to 2%, right? So it's increased by 1.5%. We can also look at this on a relative scale. The probability of disease for exposed was 2% divided by probability of disease for unexposed, which is 0.5%. The 2% divided by 0.5% is 4. So we can say those who are exposed have 4 times the risk of disease than someone who's not exposed. Right at the top is 4 times the size of the bottom. Or if we subtract 1 from that, right, 4 minus 1, that gives us 3. There's a 300% increase. The risk went from 0.5% up to 2%. It increased 300% on a multiplicative or a relative scale. This is one of the key things to take away, that the attributable risk versus the relative risk, they're two slightly different lenses of looking at the same problem. And they can sound quite different or more dramatic depending on how you make the statement. So what I mean by that is, suppose that your risk of disease, say, is 1% if you're not exposed. If you are exposed, it goes up to 2%. On an additive scale, we can say your risk goes from 1% to 2%, or it increases by 1%. On a relative scale, your risk goes from 1% to 2%. It doubles. Here it goes up by 100%. Okay, so again, if the risk of disease for someone who's not exposed is 1%, and for someone who is exposed, it's 2%, we can say that your risk is going up by 1%, or your risk is going up by 100%, depending on if we're looking at an additive scale or a relative scale. One is not intended to be misleading. The point is that these are two different lenses for viewing the same problem, and you need to be cautious with knowing which lens is being used. Is it being compared on an additive scale or a relative scale? Okay, now in the same example, the odds ratio would come out to be 4.06. So what I wanted to show here was also in this case of a rarer disease, and usually the guideline for rare is less than 5% prevalence, or there's different guidelines that are used, but around that, less than 5 to 10% is considered rare. So let's look at example B. There, if your risk goes from 10% when you're not exposed up to 40% when you're exposed, the difference between those two is 0.30 or 30%. So on an additive scale, your risk is going up by 30%. On a relative scale, it goes up to 40% from 10%, or that's 4, right? So again, an increase of 300%, or the risk for those exposed is 4 times the risk of those not exposed. And the odds ratio, if you work that out, would come out to be 6. Now in that final example, example C, where your risk of disease when you're not exposed is 20%, when you are exposed it goes up to 80%. On an additive scale, it's going from 20% up to 80%, or a 60% increase. On a relative scale, the 80 over 20 gives us 4. The odds ratio, if we work that out, it's going to come out to 16. So what I wanted to show you here was in all three of these cases, A, B, or C, the risk ratio or the rate ratio, right, the RR, is 4. It's always the same. Okay, but you can see the attributable risk is quite different, or the odds ratio is quite different. So this is just meant to kind of help you compare and contrast these a little bit. And I also wanted to show you in that example C, we can see the odds ratio starts to get much bigger than the rate ratio. Okay, so when the disease is not rare, the OR inflates, or it gets much bigger than the RR. In example A, where the disease is quite rare, you can see we can calculate an odds ratio and then interpret it as a rate ratio. Okay, but in example C, that odds ratio of 16, we don't want to say that someone who's exposed has 16 times the risk of disease than someone who's not exposed. We can see in that second column, it's actually 4. Right? Someone who's exposed has 4 times the risk of disease than someone who's not. We need to be a bit careful to make sure if we want to interpret an odds ratio the way we'd interpret the rate ratio, we need to be working with a rare disease. So what we're going to move to next is looking at how we can take these same sort of measures but use logistic regression to adjust them for confounders.
Stick around, guys. There's more to see, and please stay safe.